Okay, so welcome back, and I hope those who are participating in it made good use of the career fair and found it beneficial. This week we're going to be going through a number of topics that span actually several different languages. But the first one I wanted to begin with was a take-home exercise that I gave to you for today. This take-home exercise focused on an area that we had alluded to and talked about at an abstract level, but hadn't gone into in detail. So just to kind of put this in perspective here, what I'm going to do is to just review a little bit. So we recall we started with the challenges of complexity. We talked about the need for modularity to address this complexity, the need to put in place a divide and conquer strategy so that we have a larger problem that we break up into pieces. Each of those pieces we can assign to a different person or test readily on its own, mock out. We can replace potentially with more suitable implementations over time. And I noted that abstraction is a central key to modularity. So abstraction being the process of hiding certain details, abstracting over, and creating something that's more general. It can handle many particular cases. And this allows us to achieve modularity in part because we can have these abstractions capturing a lot of functionality used from many different places, and we could then replace that implementation of that abstraction with another one. But there's a further way in which it enhances modularity. And I noted that fundamentally there's two types of abstraction that we use. One is we create more general cases by parameterizing an abstraction. And here we're specifying the detailed context using parameters. And we saw some of that last time, right? We broke this code up into these individual functions. And each of those functions took parameters that specified much, if not all, of the information it needed to do its job, right? And by doing that, we could use that function again and again and again within the code, maybe from one static location in the code, but many times dynamically, or maybe from several locations in the code. We could make use of it at different places. So abstraction by parameterization. Today we're going to see an additional way to parameterize code using types for functions. Okay, so we're going to look at type parameterization. But before that, I'd like to discuss the take-home exercises first, often because they're freshest in students' minds just as they come in, perhaps some of them working on them even in their seats. The other type of abstraction was abstraction by specification. And here, it's not opposed to abstraction by parameterization. Typically we do both together. But it's a different type of abstraction. Why is creation of specifications, these kind of high-level declarative indications of what code does, these comments, for example, which indicate this code undertakes this job, but they hide the details of exactly how. Why is that an instance of abstraction? Why does that help us deal with many particular cases? Anyone? Yeah.
You don't need to know the particular cases, you just need to know what goes in and comes out.
Yeah, and the particular case here is the implementation. So that one abstraction is defined by the specification, lets us swap in, put in place different implementations of that. They all adhere to the same specification. They all adhere to the same statement of what this code does, even though they accomplish it in different ways. Right? Yeah.
So this is in effect a code specification, just like ISO 9000 is a process specification.
You could think of it at high level, kind of similar, but the goals of the specification and the way in which it operates strictly during the ins and outs of programming are a little bit different because it needs to be something that's digestible very quickly, almost at a glance, and contained fully within a small bit of space within that code base. Now, at some time, there are times where these specifications become larger, actually. They become more extensive. And when we talk in this class down the road about specifications as they apply to classes, to class level abstraction, not just function level abstraction, they're going to actually become more intricate. They've got to deal with the fact that this class can be subclassed and what are the safe conditions under which it can be subclassed. They have to deal with invariance and history properties, and often they become more extensive. We'll provide subtyping specifications or subclassing specifications, as well as specifications related to the small details of particular methods. And there you can get more fulsome specification, but even so, it's not going to be at the level of an ISO document. It's going to be smaller than that. But the basic idea here is similar in the sense that that one specification can handle many particular cases. And I want to draw a distinction here. This is a very important distinction. Abstraction by parameterization, that abstraction is helping the clients, the users of this abstraction, use it from many different places, right? They can call it from here, they can call it from there, they can call it in this case, this variant, etc., just by changing the parameters associated with it. Abstraction by specification gives flexibility to a different party. To whom does this give flexibility to? To the developers of the abstraction. It allows them to evolve this unit of code in a viable way. So it allows them to put in place new implementations of it, etc. Okay, so those are our two key components, and this gets us to this issue of specification for the code. That we've been talking about, the code that we've been putting into place here. So, without further ado, I think what I'll do is call up the examples of the code. So I created, as I want, a solution of my own to this exercise. And I'm going to walk through some examples in this of specifications that I put into place. Without claiming that they are privileged in the sense that they're terribly, terribly deeper or profound, but they are practical. And what they include is certain types of information that would be very important at a practical level, okay? And I want to highlight certain types of that information. So here we're dealing with specifications for bits of code. And you'll see that these specifications are provided in comments, okay? That's not always the case. There are programming languages out there, and in your professional careers, these are going to become increasingly common, where these specifications will be placed not in simple comments for human consumption, but in fact in computational structures which the compiler will understand and know about, okay? And we'll be seeing, not too long from now, in a different programming language, Scala, how some elements of that are supported, okay? How we can capture specifications in a way that is declarative. They indicate what needs to hold, for example, preconditions, postconditions, but does so in a way that a compiler can help reason about or check, okay? We're going to be seeing that. Here, they are specified in comments. And as such, we have merely conventions to guide us as to how these comments might look. In another language, let's say Java, we might put these in Java docs, right? use Java docs to sort of document these functions. So here, what we're specifying for these, for each of these functions is properties that the functions guarantee under certain conditions. These are preconditions, right? These state, for this function to do its job, I need these things provided to me. Note the conditionality of that statement. I guarantee the postconditions if the preconditions are met. It makes no guarantees of what I do if those preconditions aren't met here, okay? And generally speaking, that's part of this contract. Just like FedEx doesn't promise you what it will do if you don't, adhere to certain guidelines about a package or what have you. They can't guarantee, safe delivery if it isn't properly wrapped or what have you. The preconditions are sort of caveat emptor. These are things, if these are guaranteed, I'll do my job. If they aren't, I'm not going to provide these promises. Yeah. So.
That's a syllogism. That's a syllogism. If your code is valid, it compiles. If the conditions are met, the postconditions will come out.
That's true. Yeah, that's exactly right. And if they're not, there's generally no guarantees. Although sometimes the specifications will, in fact, indicate some, that an exception will be thrown or something like that, or an empty array will be stated. It's just that these preconditions, these are up to the caller to guarantee. Okay. Now, there is a mechanism that we make use of, and I mentioned it in 371 for those who are in that class this semester or have been in the past, by which these preconditions are actively checked routinely within code. What's that mechanism?
Asserts.
Asserts. Yeah, we put in place assertions that state these preconditions and that state these postconditions at the time that the code is completed. Now, these preconditions commonly refer to, and here they certainly do, the parameters, right? So here we, for example, have an indication that argc is greater than or equal to 1, and argv is the length of argc. Notice that each of these is specifying some property about information that obtains when the method is called. It's something that up front can be checked here, right? So it's about these two arguments. And notice that that specification is not about each argument in isolation. It can refer to relationships between the two. That this one has a number of entries equal to this, for example. So it's not that you're specifying the property of each of the parameters in isolation. It's the interaction is also important. Okay. Now. Given those conditions, then we provide some postconditions. And these postconditions are sometimes stated outright. For example, this one down here where we say run scenario. Here we say, returns a certain well-defined value. Returns a pointer to the final state of the model, encoded in the same row major order as was buffer even. The final state is produced by running Conway's game of life for count steps starting with the initial state of the model. So here we're making a statement about what it is that we returned. And that can be sharpened some, but the point is that it's a specific guarantee that holds. That guarantee is provided outright. In some cases, we may make a conditional guarantee, or it may be contingent under different situations. So if no command line argument is given, i.e. if argc is equal to 1, this runs Conway's game of life for default iteration count iterations. If one command line argument is given and it is a positive integer, encodable as an integer, it returns Conway's game of life run for that number of runs. If more than one is specified, then such and such holds. So these are postconditions which indicate what this does, right? What job it performs, not how, but what. It doesn't say all the details, for example, here about whether it's using bit vectors for its implementation. It doesn't say exactly how this double buffering is carried out. It's just providing an overall guarantee of what is what is ensured. And that allows us as creators to change out the implementation. Because someone who's using this code should be counting on this, not this. Right? They shouldn't be counting on the implementation. If you're counting on all details of the implementation, all bets are off about whether your code will break when that implementation evolves. This provides a contract that helps ensure what the users can count on, and conversely, what the people who created it can evolve. Right? Simple enough, and it's an abstraction because it provides for many possible implementations which will meet this specification. We're going to see these specifications again and again and again in different contexts, different languages, and in fact different types of abstraction, such as with class-based abstraction or aspect-based abstraction. Okay? So the overall idea here is a simple one. Provide contracts that guarantee what and not how of code. Now, that being said, there's a couple other aspects of this I want to hit on. One thing is that these guarantees are not always purely about the argument. Sometimes they are. Sometimes the relationship is purely a functional one, and I use the word purely there with a bit of punning. It's a pure function of the arguments. So here, for example, compute liveness. Here, I take and I'm specifying a rule for whether or not this cell is going to be alive in the next round based on whether it's currently alive and the count of ones around it that are alive. And there's a simple rule here involving these for Conway's game of life that specifies whether or not it's alive. Here, it's purely a function of these two arguments. But there are cases where the code is not going to be a function purely of the arguments. There's something else that it could depend on. And what is that thing?
The state?
Yeah, the state of the system as captured here in what? It's captured here in these sort of things. Global data structures, right? That's a type of information that obtains when this code starts that is not merely reducible to the parameters. It's not passed explicitly via the parameters. It is being used by this code or can be seen by this code, but can't directly be seen as part of the parameters. And yet that is part of potential preconditions, right? We could have a precondition that basically states, that buffer even has to contain a legitimate state, for example. And so that is well within the purview of preconditions. They're not purely about the parameters here. They could specify some state as associated with global data structures, as associated with the state of the frame buffer, of the screen currently, or what have you. Okay? Important point. Second point, related to that, is postconditions are often about the return value, but are sometimes about other things. What other things might they be about?
Side effects.
Yeah, the side effects. And within the realm of specifications, there's different conventions for clarifying what the post conditions are. Sometimes you get statements of modification, what this code modifies, okay? The modifications associated with this code, rather than the conditions that obtain at the end. And that sort of boils down what is touched by this code, other than the value that it returns. So post conditions often most directly specify the return value, but they often specify more than that in terms of side effects. What other sort of side effects might there be besides the fact that it munges, that it changes some data structure, some global data structure. What other sort? Yeah.
You could change something that's passed into the function directly.
That's true. That's true. Where do we see that in this code?
Pass it return pointers.
Yeah, we pass it return pointers. So, by and large, this code is actually fairly functional. I've sort of isolated. I've isolated a lot of the need to sort of refer to global data structures by passing around information on what I refer to. But you'll notice this. Determine current and next cells. What is this doing? What is this doing here? So here, well, in order to determine what it's doing, it's good to read the specification, right? Determines the arrays to use to encode the current state at time I time. Specifically sets star p array current cells to hold a pointer to the current array at that time. In other words, this array holds the value of the current state at that time. And it's going to set the contents of another pointer, p array next cells, to hold a pointer to the next array to use. So these two items here, which are being passed as int double stars, a pointer to an int, in this case, a pointer to an array of ints, these are actually being used conceptually to do what? I referred to it earlier, too.
Pass back returns.
Yeah, pass back returns. Pass back two return values. And in C, unlike some other languages we'll be seeing, you're limited to one return value directly. And the alternatives are varied. You could pass back a structure that has, 2 pointers in it. You could pass back an array that has 2 pointers in it. You could take 2 pointers and assign into them. And there's different sort of views of what's best for that. I don't have a particularly strong view, but the point is here these are being used functionally to return 2 values. And because they're being used functionally to return 2 values, they are part of the post conditions. We are setting the contents of these values to point to something, right? So that's good. This code could also modify data structures, but it could also do something else. It could, other types of side effects. It could send a message over, it could make a connection. It could send a message, an email message to the creators reporting a bug. It could update the current graphics to show, an updated scene or what have you. The point is those are all side effects, okay? And side effects need to be documented as part of post conditions. You need to say this was performed. A final thing that I will say that's extremely important is that the preconditions and postconditions collectively need to include something about not merely the functional form, the kind of mapping undertaking, at a high level that this takes 2 ints and returns a double or something like that. But it needs to say what it does. What job does it accomplish? That, this takes the square root of the number passed in as the first argument to the level of precision specified by the second argument. That's a relationship. It's a specific relationship. And it happens to return a double. Let me ask this. If you substituted, if you had a specification which said that, and you substituted a cube root routine, would it match? Is that a valid implementation of that specification? Let me say that again. If you had a routine that took the square root of a number, provided as the first argument, to a level of precision provided by the second argument, and it returned a double, and you had a specification that indicated this, could you just substitute a cube root routine? Is that a valid implementation of that? No, I want to emphasize. Maybe it seems obvious, but the point is, don't get caught up that, oh, this is something that takes two doubles and returns a double. Yes, it is, but it's a very particular function. It's one that takes the square root. You know, cube root is not going to cut it. You know, something that takes the first argument, you know, to the power of the second argument, it's not going to cut it. It's not a valid implementation of it. The specification has to say something about what it does to rule out those cases, what it is accomplishing in functional terms, what the job of this thing is. And that limits the set of possible implementations. And it should. Because your code's going to break. If this thing performs the square root operation and your code is counting on that, and you know, maybe to determine, you know, maybe you know it's a square area you're dealing with, and you determine the sides from that, the length of a side, each of the sides. And if someone substitutes the cube root routine as the new implementation of that, your code is going to break, right? It's very practical stuff, folks. I mean, this is about how to prevent code from breaking unnecessarily as we change our program. That is why we create these specifications. Because if we have function A, depending on all the gory details of function B, function A will almost certainly break when function B changes, or will often break. It'll break because it's counting on some unspecified details of function B, and when function B changes, those could break at any time. So this is all about limiting to very well specified conditions what A counts on in B, so that B can evolve independently of A. Yeah.
Another example where you can break, if you put a cube root implementation, it can return a negative number.
Yeah,
Where
exactly.
the square root can't, and therefore if you're
Yeah.
counting on it not being negative.
That's right. And let's be clear here. If you say this returns the square root, thank you, Scott. If you say that this returns the square root, and you know it's specified such that that's a clear thing, then a user could reasonably infer that it's always 0 or more. So we have to be clear here, and that's perhaps the final point I'll make here, that with specifications, there's what we say here, but there's also, you need to consider what are the users going to infer from this? What are they going to take away as logical deductions from this? Because the people who use our code are probably going to be very bright people. All they're going to have to go with often about our code is not the code itself, which might be in a binary library, a jar file, or what have you. They will have the specification. And they will study that specification and make inferences that are sound from that. They will say, oh, okay, so it's that sort of mapping. The value that it returns will always be greater than or equal to 0. Or, oh, okay, so that's what it does. It searches in the collection I provide for the first element, you know, in order of indices that matches this one. So it doesn't modify that data structure. So I'm going to assume that actually that when I call this method, it returns a value that my data structure is unchanged. So they're going to make inferences from your code about what, even though it doesn't state it explicitly, the fact that it has stated it in a way that seems to rule out that behavior, they are going to make come to conclusions because of that. So if there's ambiguities in your specification, or there are areas where you don't want to make guarantees, you don't want to ensure, you know, this certain thing, you want to give yourself flexibility to change a certain thing, you need to specify that here as part of it, or else they may come to conclusions otherwise, okay, about things that are reasonably up in the air. For example, if your code says it returns an index to something which matches the predicate provided within this collection, you may want to state that no guarantee is given about whether it's the first or the last such index or what have you, some index. And make that very clear so that the people who use it don't come to a certain conclusion. So there's a certain circumspection that comes here about trying to make sure that people aren't counting on things. Another example we'll be seeing later is providing indications as to whether or not there are side effects in the underlying data structure of certain types. So if you have a implementation that right now seems to be immutable, and you don't want to guarantee that all future implementations will be immutable, you may want to state that explicitly in the specification, okay? Or else people could reasonably look at it and say, okay, this is never going to change, given that specification. So you have to be careful of not only about what's stated, but what's not stated, and be thinking about ambiguities. Another thing is, when you use certain words, they might be subject to different interpretations in different cultural contexts. People from around the world will use different terms for things. A lot of my students from South Asia will say, A by B to mean A divided by B, for example. And that's not a term that we here in North America tend to use a lot, but it's something where if you're putting into place a specification that uses certain words and you're dealing with global customer base, you might want to put in things like IE, or give an example is one of the best things you could do. Give an example, this applied to that will yield that, to make it less ambiguous. So you need to be aware words have different implications. Billion, million. These are words that we may use in a certain way, but our cousins over in England might use in a different way. Okay, so you need to be careful with the global base to put in place enough clarifications. In other words, explanations or examples that will lower the risk of ambiguity. We live in an imperfect world. We need to write specifications that are small enough to be consumed quickly. They won't overwhelm someone, but are large enough to help reduce the amount of ambiguity. But fundamentally, we are dealing with the limits of human language. But the goal is to try to lower the risk of misinterpretation to a reasonable enough level that we reduce, dramatically the number of bugs that could come about because people are counting on our code and we evolve it in a way that they don't expect. Okay. Any questions about this issue of specifications? Did you folks find any particular challenges or things you struggled with these specifications? I will, of course, provide this. Anyone find challenges? Okay, yeah.
Just wondering, where do you specify what the parameters mean?
Well, good question. So, so here, there's a couple places, right? And we will specify typically properties associated with these parameters here, but also within this statement here, there's often references to the meaning. So, for example, let's take a look at this one. Preconditions here are 0 is less than or equal to time, or time is greater than or equal to 0. You could have written it. And this says determines the arrays to use to encode the current state at time I time. Okay, so here I time is being specified to indicate a certain time. Probably it would be good if this had further said, I time is a time step. And this really should have said I time. I time is a time step starting at 0, for example. That would have been a good thing to say in preconditions, but often elements of that are placed into the specification above in a way that provides some explanation here. And you'll notice, for example, we specify functionally how these elements serve, and that provides some indication of what role they play. So here, for example, sets p array current cells, star p array current cells to hold a pointer to the current array at that time. Okay, so here we're saying what job this accomplishes. I think that a reasonable critique of this particular one is that I could have provided more information, and you'll notice that I've done that here. For example, row is something that is between these elements here, and I specify here that it's the name, the number of the row. But I probably could have provided even here more information. So it is a good practice to say, okay, what is the meaning of this? What's the semantics associated with this parameter within this precondition area? But often it is provided within the specification itself. Okay? Okay, other questions on this? Specifications are good, they're going to follow us through the class. And for those of 371, you're going to be putting in place specifications there. And I'd expect, similar attention to preconditions and postconditions, but in the object-oriented context, we're going to be dealing with history, properties, and variants as well. Okay, so these are properties being ensured as part of by this code. They are contracts, and they allow this code to evolve. Okay, yes?
It also looks like you're totally avoiding like saying what kind of type each variable is in the conditions and the post.
Well, okay, so that's a good question. The type is specified here, okay? And, to the degree that that's complex, that could be folded in here. For example, if we're dealing with a array of pointers to functions, maybe that will be something that will be mentioned up here, that this is an array, each of whose elements is a pointer to the function. But generally speaking, the type signatures here are going to tell you a lot about the types. All I'm saying is when it comes to complex types, we might specify more information. That might be something that in some contexts would be useful. For example, if you have a type def, if you have a type definition that indicates, an int double star is a array pointer or something like that, then we might further say that this is a pointer to an array in a way that would explain it, because it might not be clear from its name. But often we can turn to the signature to indicate something about the types. But if you think there's room for confusion, if you think a person could be confused, I think it's a great thing to put in there. Yeah.
So in the case where we're using, basically a double pointer to be able to return multiple values, would it be useful to explicitly state that in the specification, is that this is the reason it was done this way?
Yeah, I think that's a good critique. So here, for example, we could have said, okay, these two arguments are serving to return two pointers. They happen to be captured as parameters, but functionally they're serving to return two pointers. That was preferred for X and X reason. They should be used like this. You'll notice that there is a gap there, a notable gap. One thing I should have said that is here is that these pointers are what? These pointers should be referring to different locations, for example, and they can be overridden safely, for example. They also should be non-null, right? That's very important, that people shouldn't pass in two nulls for these and think that somehow the code's going to work, right? So these need to point to distinct things that can be overridden and they're non-null. That would have been something that would have improved this. Okay. Specifications are key to creating code that can evolve independently without pulling your hair out, without having to have every time you change B, A breaks. All right? Okay. In an open source context where you do have access to the code, are specifications still very important? Yeah, why is that?
It tells you what not to change in the
Yeah, exactly. I mean, just because you can see the code, first of all, doesn't mean you want to see the code. Often you want to look at a specification that will summarize what's going on. The second thing is you don't want your code to break at any point because it's counting on some obscure aspects of implementation of that. You know what the implementation is now, but you don't know what the implementation will be 6 months from now or a year from now. And especially in an open source context, the person who's modifying that stuff over there that you're counting on may not be you. And it may happen at lots of different times. So you absolutely want specifications even if you have access to the code base. You especially need specifications if you don't have access to the code base as well, because this is what you got. And you want to know what can I count on, what can I not count on. Okay? Specifications are key. Now, I'm going to use this opportunity, because we have some code up here and because I've got a question about it from a student. I wanted to hit on something that I would have hoped might have been captured in some previous courses, like 332, but I don't know how many people in here have taken 332, so I don't want to count on it. And that has to do, ladies and gentlemen, with an aspects of C's type system, which is going to be very important for Thursday. Okay, I'm asking you for Thursday to capture via a mechanism in C a way of abstracting away from what rules we're using, abstracting rules so that we could apply different rules than the standard rule for Conway's Game of Life, and we could see, how the board will evolve over time with different rules in place for its evolution. When I talk about rules, I'm talking about rules involving, for example, this liveness. Okay, and the way in which we allow, one big way we allow for flexibility in rules within C is through a use of something called pointers to functions. Now, how many people have used pointers to functions to at least a significant degree, either in class or in internships or other things? Pointers to functions. Okay. So I'm going to give a brief tutorial on pointers to functions. Okay. And the first thing I want to state, because it seems people go through different levels of education on C. I want to make a general, I want to articulate a general principle, and we'll apply it then to pointers to functions, okay? And the principle, and probably what I should do, is stop this recording.